Hello everyone. I hope all of you are doing well and good. In this video, we will be solving some questions of exercise 1.2. Um, and I have written down some concepts that will come very handy while solving the questions. First, we will be discussing about the concept, then we will move on to solving the questions. Now let us talk what is composite number. So composite numbers are those numbers that have more than two factors, and the prime numbers are those numbers that has exactly two factors. What do we mean by this? If we take, let's say, 8, we know that the number 8 can be divided by 1, and the number itself, which is 8, then 8 can also be divided by 2 and 4. So these are the factors of number 8. This means that this number can exactly divide number 8, and those numbers that can exactly divide 8 are called its factors. So for a number to be called a composite number, it has to have more than two factors. Only then we will consider that number as composite number. And in this case, number 8 has four factors, which is more than two factor. So 8 satisfies the condition to be called a composite number. What about number 7? We know that 7 can be divided by 1 and the number itself, and apart from these two numbers, we don't have other number that can exactly divide 7. So number 7 has just two factors. So we will consider number 7 as a prime number and not a composite number. Let me show you some examples of composite numbers and prime numbers. So number 4 is a composite number, number 6, composite number 8, 9, 10, 12. These are some examples of composite number. And as for prime, we will start with 2 and 3, 5, 7, 11, 13. These are the examples of prime numbers. Let me tell you that 1 is not a prime number, because I have already told you that for a number to be considered prime, it has to have exactly two factors, but the number 1 has only one factor, so 1 fails to be called a prime number. And one more information on prime number is that number 2 is the only number that is even and also prime. So please remember that 2 is the only number which is both even and prime. Now let us move on to canonical decomposition. What is canonical decomposition? Canonical decomposition means the process of expressing a composite number as a product of its prime factor, each raised to some power. Every composite number n can be expressed uniquely in the form n is equal to b1 to the power a1 into b2 to the power a2 into the list goes on, and our last expression here is bk to the power ak, where b1 is less than b2 is less than b3, and the list goes on. The biggest prime will be bk here, and a1 a2 ak are positive integers. So what does the definition and the expression means? Let's say, mm, let's consider one example. 24. We know that 24 is a composite number, and the canonical decomposition says that we can express any composite number as a product of its prime factor. So we'll just take prime factorization: 2, 12, 2, 6, 2, and 3. And 2 and 3, this our prime number that occurs whilst finding out the prime factorization of that composite number. So this 2 and 3 are our P1 into P2. And what is A1, A2 till AK? They are the powers of the prime number. So over here we can see that 2 occurs thrice. So we're gonna write to the power 3, while for the prime number 3 it occurs just 1. So we'll write to the power 1. Here our P1 is 2 and our A1 is 3. P2 is 3 and our A2 is 1. We just have to express the composite numbers in the form of these. This is what the canonical decomposition says. And canonical decomposition is simply the standard or unique form of writing the prime factorization. Find out the prime factorization of the numbers at the right hand side of your answer sheet. Then on your main working sheet you can express them in the form of P1 into to the power A1 into P2 to the power E2 till Pk to the power Ak. You just have to express them in this form, and this form is the canonical decomposition of that numbers. And the condition that we have to keep in mind is that we have to express our distinct prime number in ascending order. That means for this composite number 24, I cannot write 3 to the power 1 to cube. I cannot write like this. The proper definition of canonical decomposition says that I have to write the prime in ascending order. So that means 2 has to come first and it has to be followed by 3. And if there is any other bigger number, bigger prime to be exact, that will have to follow after this. That is the definition of canonical decomposition. I hope you're clear with that. We will come to know more about it in depth while solving the question. And now let us discuss what is HCF and what is LCM of any two numbers or of any more than two numbers. So our definition of HCF in exercise 1.2 will be this: the product of smallest powers of common prime factors, and the definition of LCM will be product of greatest powers of all prime factors. This will be the definition of our HCF and LCM in exercise 1.2. What does this mean? Let us let us understand the definition with example. I have taken 360 and 588 below, and I have taken the prime factorization of 360 and 588, and let me express 360 and its canonical decomposition. The distinct prime numbers involved in the prime factorization of 360 are 2, 3, and 5. 2 occur 3 times, 3 occur 2 times, 5 occur 1 times. As for 588, 2, 3, and 7, 2 occur 2 times, 3 occur 1 time, 7 occur 2 times. This is the canonical decomposition of 360 and 588. And if I were to find the HCF of these two numbers, the definition says that I have to consider the smallest powers of common prime factors. That means I have to check what are the numbers, what are the common prime numbers in the canonical decomposition of these two numbers. That is 2. First, let us check for 2. 2 I can find over here, and 2 is also here. That means I can consider 2 in our HCF, and I have to take the smallest power of the 2. So over here we have 3 as power, and over here 2 as power. I will consider power 2. Let us check for the next number. 3 is also found in the canonical decomposition of 588, so I will consider 3, but the power will be 1 because 1 is a smaller power. And as for the number 5, I cannot consider number 5 because there is no number 5 over here. And the same goes for number 7. There is no 7 here, so I cannot consider number 7 in the HCF of 360 and 588. That means my HCF will be 12. Now let us check for LCM. The definition of LCM says product of greatest powers of all prime factors. So regardless of whether the prime occurs in one number or not, if it occurs in the expression of canonical decomposition in the other number, then we're gonna take that prime number. And also we will be considering the greatest power of that prime number. So we can see here 2 will be taking the greatest power. As for 3, we'll be taking the greatest power, 5 and 7. So our LCM will be, I have solved this beforehand, so I know that the result will be 17640. If you solve them, you will get the LCM of 360 and 588 to be 17640. And in exercise 1.2, we will not be writing HCF of 360 and 588. We will not be writing like this. There is a certain notation to express HCF and as well as the LCM for any two given numbers or for any numbers. I will use first bracket to express an HCF of the numbers. Let's say 360 and 588. If I express like this, that is, if I use first bracket, then this means HCF. and if I use third bracket, then this will mean LCM. If you see this notation into quotient, then know that this is talking about HCF and the third bracket is talking about the LCM. And there's one identity that I would like to mention here is the product of HCF and LCM will give you the product of that two numbers. Suppose that two number is A and B, then the HCF of A and B and the LCM of A and B will be equal to the product of that two number. This is one identity that will come very handy while solving the question. Let us move on to question number 1, exercise 1.2. Find the canonical decomposition of numbers of the following numbers. Roman number 1, 1914. So what we will do is we will first find out the prime factorization of 1914. The prime factorization of 1914 is this, and we will express them as 2 into 3 into 11 into 29. We'll stop here. We cannot go further as 29 itself is a prime number. So, and we know that each prime number over here occurs exactly one time, so we are not gonna use any power. Let us move on to Roman number 4. 190575. Let us find the prime factorization of this number. 3, 6, 18, 3, 3 are 9, 15, 3 2s are 6, 15, 3 2s are 6, 1, 1, 7, 5, 7 times 3, 21, 2, 7 times 2, 14, 7 times 5, 35, take 5, 5 times 6, 30, 0, 5, 5, 1, 2, 1, and then 11 square. But we will have to arrange this in ascending order. So 3 will come first, after that 5 will come, 7, and then 11. 3 occurs twice, 5 occurred twice, 11 occurred twice. So this is the answer. Make sure that you are representing, or you are making sure that, please make sure that you write down the prime factorization properly at the right hand side of your working of your answer sheet, and then express them in its canonical decomposition properly on your main working sheets. Moving on to question number 2. Find HCF of A and B, LCM of A and B, and verify that the product of HCF and LCM is equal to the product of the numbers. For Roman number 1, our first number is 429 and our second number is 715. The first thing that we will do is we will find out the prime factorization for both the numbers. Let me quickly complete the prime factorization. 1, 11, 3, 10, 11, 11 times 1, 11, 11 times 3, 13. For 715, this would be 5, 1, 5, 2, 20, 3, 11, and 13. Now, I will express them. Let's write 429, 3 into 11 into 13. For 715, it is 5 into 11 into 13. So this is the canonical decomposition. And to find out the HCF, I will need to use the first bracket, and then I will have to determine what are the prime numbers that occur in both the canonical decomposition. 3 is here, but we do not find 3 here, so 3 fails to be part of the HCF. We can find 11, 11, 13, 13. So we will take 11 and 13. 11 and 13, the product is 143. That means our HCF is 143. Now let us find the HCF. We will be using the third bracket, 429 into 715, and we'll be using all the prime numbers that appear in both the canonical decomposition. That means we will use 3, 5, 11, and 13. 3 and 5 and 11 and 13. The product will be, this will give you 15, and this will give you 143. If you solve 15 and 143, you will get 2145. This is the product. Now we will have to show that the product of HCF and LCM is equal to the product of 429 and 715. Let us write them properly in words. We'll have, or we need to show that, we need to show that instead of using A and B, let us use the number. $715 is equal to 429 into 715. Left hand side is equal to, what is our HCF? Our HCF is 143 and our LCM is 2145. Now if you compute the product of 143 and 2145, you will get 306735. This is our left hand side. Now let us solve for right hand side. 429 into 715. If you compute the product, then you will get 306735. Comparing, left hand side is equal to right hand side, hence shown. This is your question number 2. I hope you're cleared with the solution. If you have any doubt in understanding any step, any part of the explanation, you can write them in the comments. I will make sure to address them in the next video. Moving on to Roman number 2, our A here is 756, B is 1044, and I have expressed 756 in its canonical decomposition. Same for 1044. first bracket indicates HCF. I need to find out the prime factors that occurs in both the canonical decomposition. I can see that 2, 2 and 3 occurs in both the numbers, so 2 and 3, and I have to take the smallest power. So 2 and 2, they are equal, so I can just take 2. 3, the power here is 3 and the power here is 2, so the smaller number I will have to take, that is 2. Now 2 square into 3 square will give us 36. 36 is our HCF. And our LCM, I have to take all the prime numbers that occurs in the canonical decomposition, and I will also have to take the greatest power of the prime numbers. 2, 2, the greatest power is 2. For 3, the greatest power is 3, so I have taken 3, 7 and 29. The power is 1. If you compute the product, you will get to 192. We have complete first part of the question, that is the HCF and the LCM. And now we have to do the verification, that is the product of HCF and the product of LCM is equal to the product of the numbers. The HCF is 36, the LCM is 2192. If you compute this product, you will get 789264. And if you just simply multiply 756 and 1044, you will get 789264. They are the same, hence we have shown that the product of HCF and LCM is equal to the product of the numbers, hence verified. This is our Roman number 2. Let us solve question number 3. Find the HCF and LCM of the following integers by prime factorization method. Roman number 1, the numbers are 204, 1020, 1190. I have expressed the numbers in their canonical decomposition form. You can find out the prime factorization on your own, but this will be the canonical decomposition of the 3 numbers. The question says to find the HCF and LCM. So for HCF, I have used the first bracket, which is 2 into 17. This will give me 34. For HCF, I have just taken those prime which are common in all the canonical decomposition, and I have taken the smallest powers of them. For LCM, I have taken third bracket to express that we are finding out the LCM, and I have written down all the prime numbers that occurred in the prime factorization of all three numbers, and I've taken the greatest power of the prime numbers, and this gave me 7140, and I have concluded that the HCF is 34 and the LCM is 7140. I hope that was easy. Now let's move on to question number 4. Question number 4 says the HCF and LCM of two numbers are 27 and 29295 respectively. If one is 837, find the other number. Okay, let us let A be 837 and let B be the other number. That means 837 and B. This represents the HCF of two numbers. this is 27, and 8, the LCM, which will be expressed in third bracket, is 29295. These are given, and we need to find the other number, that is B. We know that, so we have an identity that says uh, the product of HCF and LCM is equal to the product of the number. We're gonna use this identity. Our A here is 837, then our B, we are not sure about our B, so we are trying to find B here. 837 B, then this will be equal to the product of 837 and the other number, which is B. It's given that HCF is 27, LCM is 29295 is equal to 837 into B. We can transpose B over here and we will be left with 27 into 29295 divided by 837. 837 times 31 is 837, and 31 times 945 is 29295, so our other number is 945. You can conclude by stating that the other number is equal to 945. That is our question number 4. Let us solve question number 5. Question number 5 says, show that for any natural number, the digit in the units place of 3n cannot be even. So what does the question mean? First, let us see what is our 3n. It says that our n is any natural number. Let us try to substitute each natural number here and let us observe the pattern that we will get. Now if I substitute n is equal to 1, then I will get 3. If I substitute n is equal to 2, then I will get 9. If I substitute 3, then 3 cubes are 27. If I substitute 4, then I will get 81. If I substitute 5, then I will get 3243. If I substitute 6, then I will get 12, 729. Let us observe the pattern. Here, when n is equal to 1, I'm getting 3. And 3 is our units place over here. 9 is the unit digit. 7 is the unit digit. 1 is the unit digit. 3 is the unit digit. 9 is the unit digit. The question is saying that when we substitute n as any natural number, then the units place, the place that I have underlined there, or units place, it cannot be even. That means it will not be in the form of 0, 2, 4, 6 or 8. And we have observed that the unit number, the units digit, the digit in the units place, they are all odd number. So we have shown that this unit the digit in the units place are not even. And also I would like to mention one thing, that is, um, after 3 to the power 4, the pattern repeats again. That is 3, here the digit in the units place is 3971, and after this it will repeat again 3971. After this it will repeat again 3971. You can check that for yourself. uh, I will mention that in the next slide. Let us write here, mm, unit digit. Unit digit is equal to 3. Unit digit is equal to 9. Unit digit is equal to 7. Unit digit in bracket, you can mention this in the bracket. Unit digit is equal to 1. Unit digit is equal to 3. And then let us also mention that after 3 to the power 4, the pattern repeats. The pattern repeats every 4 terms. 4 terms, that is, first the unit digit will be 3, and then second 9, 7 will come, 1 will come, and then after 1, 2, 3, and 4 terms, the unit digit will become 3 again, 9 again, 7 again, 1 again, and then it will goes on. So in this way, we can see that all the digit in the units place, they are all odd and they're not even. So hence we have shown that for any natural number n, the digit in the units place of 3 to the power n cannot be even. We have shown that, but let us write them properly in a statement. Hence, the possible unit digits of 3n are 3, 9, 7, or 1. It can be one of these 4 numbers, and all these 4 numbers are odd. Therefore, the digit in the units place of 3 to the power n can never be even. It can never be even for any natural number n. I hope you are very clear with question number 5. We will continue rest of the question in the next video. Please do consider subscribing to the channel, and also share the video to your friends as much as possible, especially to those who are going to appear metric board exam. Thank you very much for watching.